Hey everyone, welcome back to another session with OneClass. My name is Bassam. I'm an engineering graduate, and today we're going to be going through some physics problems at the high school and preliminary university level, and we're going to be verifying some solutions to these problems. So let's get started over here. Switch screens here. Okay. So this is question number 1. So question number 1. Okay. Just give me a second over here. Okay, so question 1 says a 28 kilogram block is connected to an empty 2.2 kilogram bucket. So we have a block which is 28 kilograms, and then we have the bucket which is 2.2. By a cord running over a frictionless pulley, the coefficient of static friction between the block and the table is 0.41. So coefficient of static friction, that's the key word over here, and the coefficient of kinetic friction between the table and the block is 0.32. So kinetic friction for the coefficient of this is 0.32. Sand is gradually added to the bucket until the system just begins to move. So this is also key to the question, that the system is just beginning to move, so we have to think about it with relation to static friction. So we're given 2 questions. Part A is asking what is the mass of sand added to the bucket. So what is this mass as the system begins to move? So this has to do with the static friction. And then what is the acceleration of the system? So when it starts moving, what is the acceleration? So this has to do with the coefficient of kinetic friction. So let's run through what the junior tutor answered here. So a good idea always when you're starting off with a question is to list off the givens. So given mass of bucket 2.2, so it is just up here, and then 28 kilograms mass of block, coefficient of static friction, coefficient of kinetic friction, and we have those. So this is the mass of the block, and then coefficient of static friction and coefficient of kinetic friction, and those are correct. Okay, so part A. The block is at rest on the table. The weight of the bucket will pull the cord, adding tension to the cord. This tension pulls the block horizontally. Thus, the downward force of gravity is converted to horizontal force on the block, but the block will not move due to the static friction force between the block and the table. Sand is gradually added to the bucket, increasing the overall weight of the bucket. The block will not move until the static friction force by the table is overcome. Once the weight exceeds the static friction force, the block will start moving. So this is right here the equation of static friction. And they go on to defining the forces equation related to this system. And they end up with the solution of 9.28 kilograms. So let's go through that actually. So here, just think about the system overall. We can think about that there's a force of friction that's in this direction. So if I'll draw the system over here. So we have the box and the bucket, something like that, and some pulley here. So here the force of friction is acting in this direction, and we know there's a force of tension pulling over here, and then there's another force of tension pulling this way on the bucket. Really, we can think about this system as a whole. We know that the force of gravity is acting at, or acceleration due to gravity is acting downwards, so it's pulling the bucket down. And we know that this system is connected all together, so when we're using the equation F net equals ma, we have to think about the acceleration on the entire system and then the mass of the entire system. So here we can define kind of 2 variables. The first being Fw and Fs. Fs is the force of static friction, and then FW is the weight or the force of gravity pulling this down. So here we labeled it FG. Let's relabel that as FW. FW. We can equate these because although they're not pulling in the same direction, we know this pulley over here kind of changes the direction of the force, and we know that this force is balancing out this force. So since we know on this side of the free body diagram for the bucket there's a force of tension that is equivalent to the force of tension on this side of the free body diagram. So we can equate this over here, and then what we have to do is just solve. So here we know that FW is the mass times gravity, the total mass, so the mass of the bucket and the mass of the box. So I'll write this as MT times gravity, and this is equivalent to the force of friction. So here let's relabel that actually. So this is actually Fs. So we know the force of static friction is the following equation. It's equal to the coefficient of static friction times the normal force on the object, and the normal force points in this direction. And the normal force is always opposed by the force of gravity on the object. So we have another force of gravity. We'll label this as Fg for the box. So knowing this, we know that the normal force is equivalent to the force of gravity because they kind of balance each other out since the object is not moving in either direction. And we can say that we have the coefficient of static friction, and then we have the normal force, which is just mass times gravity. So in this case we have the mass of the block. So I'll call this M1, and then this is M2. So mass of block times gravity. So just evaluating this, we can see that the total mass, actually the mass of the bucket and the sand, so everything on this side. So here it's not the total mass of both objects actually. So let's go back here. I'll erase this. So really it's only mass 2 here. And mass 2 is comprised of the sand that's being poured in to the bucket and the bucket itself, and we know that this is 2.2, which is the mass of the bucket plus the mass of the sand. We'll call this MS times gravity. So we can see that gravity on both sides of the equation cancels out, so we can actually just erase that. We don't really need that there, and then we can just equate this to the coefficient of friction, static friction, and then we can erase this as well. We don't need this equation anymore. So we have 2.2 plus mass of the sand that's being poured in is equivalent to the coefficient of static friction times M1, which is the mass of the box. So we can say the MS is equal to, what was the value? Coefficient of static friction is 0.41. Times M1, which is I believe that is 28, and then subtract 2.2. So we just moved the 2.2 on this side and put it to this side. We subtracted from both sides, and when we evaluate this, let's plug this into our calculator. 0.41 times 28 minus 2.2, we end up with 9.28. is kilograms. So yep, we get the same answer. So we can say that this part of the solution is correct, and 9.28 kilograms of sand is added. So here really we kind of translated that. Just looking at this diagram, we can see that this force has to kind of balance out with this force based on the tension. You can draw the free body diagram for each part separately, but you'd have a more an unnecessary, more complex solution. So here, this is the simplest way to think about it. You set the two forces equal, and then you kind of evaluate based on the givens. So when we have the second part of the question, so part B, so let me clear the page here. So we have part B. So here we're asked the acceleration of this. Oh no, that wasn't the question. The question's up here. The question is, what is the acceleration of the system? So here we have to think about it with regards to the force of kinetic friction. So here the junior tutor presents the correct equation for force of kinetic friction, and then they kind of use the equation F net equals ma. So the net force acting on the system is mass times acceleration, total mass times the acceleration. So we can rearrange and we can say A is equal to F over M. And then we have to kind of figure out what is F, what is M, and what acceleration does that give us. So F can be solved here with this equation. So we've already defined Fw and Fk in the previous question, but we can write that out. So the numerator will be Fw minus Fk, and this is mainly based on the diagram. So we have the weight acting down, and then we have the force of kinetic friction. You can also think about it kind of from this block. So you can think about the force that's pulling this down is also over here as well, and it's going to be pulling it as well in this direction. So that's why we have Fw as positive, because it's going in this direction, and then Fk is negative because it's going in the opposite direction, so from right to left, from in that direction. And we end up with the numerator being Fw minus Fk, and then for the denominator, essentially it's all the masses of the system. So the mass of the block, the mass of the bucket, and the mass of the sand that's going in. And the mass of the sand is what we calculated in part A. So it's 9.28 kilograms. So we have mass of bucket. So I'll just write as we said in the previous question, mass of bucket is M2, and then mass of sand is just MS, and then mass of block is M1. So here we can see in the junior tutor's answer, they kind of just do mass times gravity for the first part. So we can think about looking at this bucket. We only really have the force of gravity acting on this, and it's pulling it down. So Fw would be mass times gravity. In this case, we have two components to this, the bucket and the sand, and then the force of kinetic friction will be the same as calculated before, but with the kinetic coefficient of friction instead of the static coefficient of friction. So this is just kind of plugging the values in. So we have M2, which is the mass of the bucket, plus MS, which is the mass of the sand, times the acceleration due to gravity, minus the second component, which is the coefficient of kinetic friction, times M1 times gravity. And this is divided by. So essentially 2.2 plus 9.28 plus 28. So really, you don't, at this point, when you get to this equation right here, you've done most of the work. The remaining steps are just plugging in the values that are given and just, plugging in what each variable represents. So here we know that Fk is force kinetic friction is this, Fw is this, and then here we just have to plug in all the values. So I won't write this out, but I'll just verify that this is the right way. So 2.2 is M2, yep, 9.28, and then M1 is 28, and then they have the 9.8 at the beginning. So let's just plug this into our calculator. So we have 2.2 plus 9.28 times 9.8, And then we have minus coefficient of kinetic friction 0.32. Let's just double check that that's the correct number. Yep. Times 28 times 9.8. And then we have divided by 2.2 plus 9.28 plus 28. Okay, so I got 0.626 meters per second squared. So they got 0.51. So I'll just double check the math on this. 2.2 plus 9.28 times 9.8 minus 0.32 times 28 times 9.8 divided by 2.2 plus 9.28 plus 28. Okay, so they've done the correct process. They just this is a miscalculation. This should be 0.626 meters per second. So correct process and correct solution for part A. Miscalculation in part B. Answer should be 0.626 meters per second squared. Okay, so yeah, so it's only the second part that's incorrect. The first part's correct. So I'll mark this as correct because it's correct for the most part. And then we'll move on to the next question. Okay, so question number 2. Okay. Alright, so question number 2. Here we're asked, assume everyone in the US consumes one soft drink in an aluminum can every 2 days. Okay, so aluminum can every 2 days. If there are 330 million Americans, how many tons of aluminum need to be recycled each year if each can weighs 1/16 pound and 1 ton equals 2,000 pounds? So how many tons of aluminum need to be recycled? So they've given us some values, and we kind of have to use conversion factors and rates to figure out the final answer should be in tons of aluminum each year. So I'll write that down. We want to know how many tons per year. That's our goal. So this is a good first step to think about it. Okay, what is the end goal we're looking for? So looking quickly at the junior tutor's answer, we can see that they've kind of gone step by step. Let's just think about this. So the first thing that we're given that's easy to think about is the 330 million Americans. So let's just write that down. 330 times 10 to the 6. So that's in millions. And we want to see what can we multiply this by to get us to the final conversion factor. So we know this is Americans, so I'll write A for Americans. And then the next component, one soft drink in an aluminum can every 2 days. So one soft drink, so I'll say times 1. I'll put these just vertically on top of each other. We'll say 1 can per 2 days. I guess per American. I'll say per A. Okay, so that's pretty clear. So one soft drink per 2 days for each American. How many tons of aluminum need to be recycled each year if each can weighs 1/16 pounds? So we know we can multiply this by the conversion factor of 1/16 can. Actually, no, not can. I'll erase that quickly. So 1/16 pound, so lb per can. So the reason I want the can on the bottom is because firstly, that's how it's given in the question, but also because I want to cancel out the cans over here, because we want to end up with tons per year. So I want to cancel out all the rates that can get me to tons per year, And then finally, we have 1 ton is equal to 2,000 pounds. So we have the pounds on top. We want the pounds on the bottom to cancel out. So we'll say for 1 ton, we'll say times 1 ton per 2,000 pounds. Okay, so looking at this, we can see that, so this is all multiplied together. So this multiplied by this multiplied by this. So you can think of them all being side by side. We can see that the cans cancel out, the pounds cancel out. We have the tons left in the top of the fraction. The Americans cancel out, and then we're left with days on the bottom. But we want year. So we can multiply this by the number of days per year. So 365 days per year. So we can see, I'll use a different color. Okay, so we can see that right away we can cancel out can, pounds, days. So think about them. We're canceling anything in the numerator versus things in the denominator. So this is in the denominator, this is in the numerator, they can cancel out. This is in the denominator, this is in the numerator, they cancel out. Cans in the denominator, this is in the numerator, they cancel out. This is in the numerator, this should be in the denominator because it's per American, so this cancels out. And then finally, we're left with tons and then per year. So now all we have to do is do the calculation based on just multiplying this through and just using the values in the front. So we say 330 million times 1/2 times 1/16 times 1 over 2,000 times 365. And then we'll get our final answer over here. So we'll end up with, so let's just plug this into our calculator. So 330 times 10 to the 6 times 1/2 times 1 over 16 times 1 over 2,000 times 365, and we end up with 1882031, and this is about 1.9 million. Okay, so let's just go through the junior tutor's answer and verify. So 1.9 million is what they end up with, so it's the correct answer. Let's go through this so we can see how the process goes. So 330 million Americans consume a soft drink over 2 days, which means every day half Americans consume a soft drink. So there's another way to think about it. You're doing the same thing, just converting the numbers. So they start off with 330 divided by 2 and get 165. So that's our first step right here. And then every year for 365 days, so they multiply by 365. That's what we do over here. It's 365 per year. And then they have 1 aluminum can weighs 1 over 16, and we multiply by 1 over 16. This is what we have over here. And this means for every year, 3 billion essentially pounds of aluminum is used for soft drinks. This is in pounds. We want to convert it to tons, so we divide by 2,000. That's what we do over here. So we did this all in one step, just to kind of lay out all the conversion factors and just multiply through. This is kind of a step-by-step calculation to get to the same answer. So there's multiple ways to get to the same answer. So correct answer. Great job. And we'll mark this as correct. Let's move on to question number 3. Okay, so in this question, we're asked, can the magnitude of a vector be 0 even though one of its components is non-zero? So not 0. So we have some vector. So I just draw an arrow. So this is question number 3. So some vector, we can say this is u. And we're asked if one of its components is non-zero. So we have x and y and z, so I'll just do it like that. Z, y, x. And it could be like a, let me actually undo that and draw in a different color. Okay. So you can think of a vector as kind of some in a 3D coordinate system, some kind of vector like that, pointing to this point in space. So let's just go through the logic of what the junior tutor said. So the answer is no, but the reasoning behind it is the magnitude of a vector cannot be 0 if any of the components is not 0. So this is kind of a better diagram in the xy coordinates. So we can see if this side is 0 and this side is 0, then we get the 0 vector. But if at least this side or this side has some kind of value greater than 0, then we're going to get a vector with a magnitude. Regardless of what direction it points in, it might point in different directions, but we can see that every time we do this, we'll end up with a magnitude. And you can think of the force over here. If you were to calculate the magnitude, it would be the square root of fx squared plus fy squared. So that would be the magnitude of this force. Let me just write that a little better. And then goes on to say the components of the vector are the effects of the vector in each axis, and so on. So this is the equation for the magnitude. And even in the 3D system, same idea. If at least one of these has a value, you'll always have a vector that has a magnitude. So even if it's f of x is 0, we still have f of y, and our magnitude is just in the y direction, but we still have a magnitude. So when the vector is non-zero, any one of the components of the vector can be 0. This means that the vector is acting parallel to the other axis. So that's what we see here in this example. And the same thing in the case of a 3D coordinate system. So we'll say answer is correct. Great job. And we'll move on to the next question. So question number 4. Okay, so in this question we're asked to convert from grams to kilograms. How do we convert this? So give me a second over here. Alright, so to do this conversion, we need to know how many grams are in a kilogram. So we know that in 1 kilogram, we have 1,000 grams. So this is the main thing that you have to know. 1 kilogram gives you 1,000 grams. And whenever you're doing this in a conversion factor, you can kind of do either this in this direction, you can write the fraction out this direction, or 1 kilogram per 1,000 grams. So if we had grams, so if we had, let's say, 200 grams, and we want to convert to kilograms, we'd use this, because this is gives us the grams on the bottom, and this conversion factor will cancel out the grams. So if we multiplied by 1 kilogram per 1,000 grams, we can see that the grams cancel, and we're left with just the kilograms, which is over here, and we end up with 200 over 1,000 kilograms, which is just 0.2 kilograms. So this is a quick example. So the junior tutor here gives the correct conversion factor. 10 to the power 3 is just another way to write 1,000 kilograms. So basically you count the number of zeros here, 1, 2, 3, and you end up with 10 to the power 3. So 1 gram, so they're doing it in both directions. 1 gram is 1 over 10 to the 3. So you can see that if you divide both sides by 1,000, you'll end up with just this on the bottom. And then 1 over 10 to the 3 is just 10 to the negative 3. So there's just another way to write this. And then the last thing to note is this is in SI units. And this is kind of how you do the conversion. So, correct answer. Great job. Alright. And we'll mark this as correct. And let's move on to question number 5. Alright, in this question we're asked the other way around. How do we convert 1 kilogram to grams? So in the last question we had grams to kilograms. Now we're thinking from 1 kilogram to grams. So this is, you can think about it in the same way. We know that the conversion is 1 kilogram is equal to 1,000 grams. So I'll write out the same thing I wrote before. So we can have 1,000 grams per 1 kilogram, or 1 kilogram per 1,000 grams. So if we're given the value in kilograms, let's say we're given 210 kilograms. We'd want to use this conversion factor because we have the kilograms in the denominator, and then it will cancel out the kilograms up here. So if we multiply by this conversion factor, we'd have 1,000 grams per 1 kilogram. And we can see that the kilograms cancel out, and we're left with just the grams up here. And we end up with, so 210 times 1,000, which is, I'll just write this down here, 210,000 grams. That's kind of how you do that calculation. So looking at the junior tutor's answer, so this is kind of just general, kind of just using a conversion factor to complete the calculation. You could have different weights or different kind of units of measurement, but you kind of just have to think about, okay, how do these two units relate, and which kind of version of the conversion factor should I use? What should be in the numerator, what should be in the denominator, and just multiply through to get the final answer. So here they give the correct conversion factor. So multiply kilograms by 1,000 to get the grams. So this is correct. And then similarly, they give you the opposite direction. So 1 gram is 1 over 1,000 kilograms. So correct answer. Great work. And we'll mark this as correct. Alright, question number 6. Okay. So in this question, we have the mass of the Earth is 5.97 times 10 to the 24 kilograms, and its orbital radius is an average of, 1.496 times 10 to the 11 meters. So it's giving us the radius and the mass of the Earth. Calculate linear momentum. So we can start off by thinking, what is the equation for linear momentum? So we know the equation is P is equal to mv. So knowing this, we can kind of use these two values to get the answer. Let's go through the junior tutor's solution to look at the process, and then we'll verify the solution. So the total distance traveled by the Earth in one complete rotation is d is 2 pi r. So 2 pi r is just the circumference of the orbital radius. So if we plug this in, we'll end up with the circumference, or d here. I guess they use it here. It's a distance traveled of the Earth. So knowing this, we can calculate this, and then we know velocity. So this variable over here is distance over time. It takes 365 days to complete the full rotation around the sun. So when it's talking orbital radius, it's talking about, okay, the Earth is going around the sun, and the full circle takes 365 days. So they use this for the time variable in this equation. You do the calculation, and essentially figured out what the velocity is, and then this is just the plug and chug to get the final answer. So let's go through that process. So we have the circumference, which distance traveled is 2 pi r. We're given the radius, so the radius here is 1.496 times 10 to the 11 meters. So plugging this into our calculator, we end up with 1.496 times 10 to the 11, and we get, so 9.4 times 10 to the 11, about. So to get the same answer here, so we're going to use velocities, distance over time. We know for time, we'll write this to this side, it's 365 days. But we want to say this in seconds, so I'll do this down here. So 365 days. So here they just multiply by 86,400. But I'll show you how to get to this number without having to memorize it, so you can just think about this logically. So 365 days kind of is how many days in a year. So to get it to the seconds, we want to think how many seconds are in a day. So we can start off with something simple. We know there's 24 hours per day, so we'll multiply by 24 hours per day. And then we can think about, okay, how many seconds per hour, or we can say how many minutes per hour. So we know there's 60 minutes per hour. And then now we can think about, okay, how many seconds per minute? 60 seconds per minute. So the main reason I did it this way is because I want to get to the point where seconds is the final units for this calculation. And what I was trying to do here is cancel out the other units. So days, I want to cancel out days by having days in the denominator. And then I want to multiply by this conversion factor because it has 1 day in the denominator. Now that I have the units in hours, so use a different color. So we know right away days cancel. Okay, if I multiply these two, I'll end up with hours. I want to cancel out the hours. I cancel them out with something simple. So I know this is a simple conversion factor, and the hours cancel out. And then now I want to cancel out the minutes. I know that I can use this conversion factor, another simple conversion factor, 60 seconds per minute. So this 86,400 comes from 24 times 60 times 60. So if you do 24 times 60 times 60, you'll end up with 86,400. And that's why they multiply with 365 by this number. It's just kind of a combination of all these conversion factors. So that's just how many seconds are in, I guess, per day. 86,400 is how many seconds per day. So knowing this, we can kind of go on to get the time. This is in days, so I'm going to use a different color. So we end up with 365 times 24 times 60 times 60. And we end up with 31. It's a big number. 536,000. Okay. So I'll erase this down here. Okay, so knowing this, I'll make this a little smaller. Okay, so knowing this, we have the time, so this is in seconds. We have the distance, which is what we calculated up here. 9.4 times 10 to the 11, this is in meters. So we kind of just plug this in and do 9.4 times 10 to the 11 divided by this number. So let's do that. 9.4 times 10 to the 11 divided by 31,536,000. We end up with 29,807. This is meters per second. So they end up with, yeah, 0.29 times 10 to the 5, which is the same thing as this. And now we want to use this equation to get to the answer. So P is equal to the mass. So the given mass is 5.97 times 10 to the 24 kilograms times velocity, which is 29.07 meters per second. And we end up with 5.97 times 10 to 24 times 29.807. So we have 1.78. So I'll erase this up here. So this is equal to 1.78 times 10 to the 29. So looking at this, so here, yep, they have the correct answer, and this is in kilogram meter per second. So kilograms is over here, meters per second is from this, and we end up with kilogram meters per second, and that's the linear momentum of the Earth in this situation. So we verified the solution, and this solution is correct. So correct answer. Great job. And mark this as correct. Let's move on to question number 7. Okay, so here we're just given one word, magnitude. So you can just kind of go over this topic and kind of when is this relevant. So let's go through what the junior tutor said. Magnitude is the numeric value of physical quantity when it is expressed. It may have values of negative infinity to positive infinity. In math, the magnitude or size of a mathematical object is a property that determines whether the object is larger or smaller than other objects of the same kind. More formally, an object's magnitude is displayed result of an ordering or ranking of the class of object which it belongs. So you can kind of this is kind of a complex explanation of a simple kind of word. So magnitude is just kind of the size. You can think about it of size or how large something is, whether it's negative or positive. So whenever I say, let's say the magnitude of 2, like the number 2, so we'll label this question number 7. So let me just erase this. So magnitude of, well, let's say x, so the variable x. And x here, let's say, is 2 in this situation. So the magnitude of 2, or the size of 2, is just 2. But where it becomes relevant is if I say, what is the magnitude of negative 2? So although it's a negative number here, you only really care about the size of how negative this is. So the size of this is still 2. You kind of just ignore the negative and you just say, okay, the size of this is just 2. So that's kind of what magnitude is. So regardless of kind of what variable or what number you can get, like, let's say 1,282, same idea. If it was positive, the magnitude of this number, a second over here. So if this was positive, the magnitude would still be the same. If it was negative, the magnitude of, let's say, y, let's call this y, so the magnitude of y. So these bars right here represents magnitude. So the magnitude of y would be 1,282. So that's kind of a way to think about what magnitude is in this situation. So this answer is correct. Answer. Great job. So the last thing, actually, now that I recall something, the last thing I want to say for magnitude, let me just erase all of this. So the other thing that is important to know about magnitude is the comparison of what a vector versus a scalar. So when we're thinking of a vector, it's something that has magnitude and direction. So you have vector and scalar, and then for scalar it only has magnitude. So what does this mean here? So I'll use a different color. So magnitude and magnitude, but direction is separate, its own thing. So if we had some kind of vector, so an arrow from this point to this point, or some person traveled from point A to point B, we would say that this vector right here represents a quantity that has magnitude and direction. So the magnitude is, let's say this is like 2 meters, that's the magnitude. The direction is this person is traveling in this direction. For a scalar, really all we care about is the value of the distance traveled, not necessarily which direction. It doesn't matter which direction, we only care about the magnitude for a scalar. If the question is asking for a scalar, you only really care about the magnitude. So that's the last thing I want to say for this question. So I'll mark this as correct and I'll move on to the next question. So question number 8. Okay. Okay, so for this question we're asked, what is friction? Write its formula and steps. So we're just kind of thinking about what friction is and all its type and the formulas associated. So there's 4 types as indicated by the junior tutor. Let's go through the junior tutor's answer and then we'll verify how to think about this. So friction is a force resisting the relative motion of solid surfaces, fluid layers, and material elements. So this is kind of just a general idea. There's 4 types, so static friction, sliding friction, or kinetic friction. So I would say this one and this one are the most important ones. So I'll write that over here. So we have static, or the ones that you'll encounter the most, and kinetic. So for static is the force of friction that's acting on an object when it's at rest. So if you push on an object, you have to overcome the static friction for the object to move. But for kinetic friction is when the object is moving, there's a constant friction force that's acting on it as you're pushing on the object, so causing it to move. So I'll draw the first diagram here. So when we think about static, is a stationary object, you're trying to get it to move. So for kinetic, the object is moving, so I'll draw like streaks. It's going this direction, but there's still a force of friction resisting. So we'll call this force of friction K, force of friction S. I'll actually just write Fs and Fk. Okay. And then we have rolling friction and fluid friction. So these are also another 2 types of frictions. Usually you'll encounter static and kinetic the most. So what rolling friction is when something is rolling, when something is shaped like a circle, or when it's rolling on a surface. Rolling friction is much weaker than sliding friction or static friction. This explains why most forms of ground transportation use wheels, because rolling friction is a weaker force. So that's why kind of we have wheels on a car, because it's not as strong of a force. If you were sliding on the ground, you'd have to put more force to overcome that force of friction. You can see what this looks like in the figure. So this is just a bearing with a bunch of balls that use rolling friction when this thing turns. So you don't really have to worry about this as much, just know kind of the general idea. And then fluid friction is the friction that acts on the objects that are moving through a fluid. A fluid is a substance that can flow and take the shape of its container. Fluid can include liquids and gases. So when something moves through a fluid, there is some kind of fluid friction that's acting on it. So usually you look at these two formulas for static and kinetic friction. That's kind of what most physics problems will give you, or what they will ask you for. So two formulas are as follows. So I'll write them down here. So Fs is the coefficient of static friction times the normal force. So when we think about normal force, I'll draw another diagram. So we have some box. We have the normal force always points perpendicular to the surface. And then we have the force of gravity pointing down. So in this situation, the force of gravity equals the normal force. We can substitute this in. One thing to note is the coefficient of static friction is different than the coefficient of kinetic friction. They're two different values. Oh, I made a little mistake over here. So this is Fk here. So this value and this value are different. That's why you have two different force values for friction. The main thing to note here is coefficient of static friction is higher than the coefficient of kinetic friction. And you can kind of think about this experimentally, or you can kind of do it on an object. It takes more force to start the motion of the object than it is to keep it moving. And that's due to the coefficient of static friction being higher than the coefficient of kinetic friction. Okay, so we'll mark this question as correct. So correct answer. Great job. Okay, and this is the final question that we'll be going through. So we'll mark this as correct. Okay, so that was the final physics problem that we were going through. Hope you enjoyed this session and you learned something along the way. If you need any more homework help, or you enjoyed this video and you want to learn more, you can subscribe to this YouTube channel. Visit oneclass.com or the link in the description for any tutoring help or homework needs. So I'll see you in the next session, and hopefully you'll tune in to more OneClass sessions. And goodbye for now. See you later.